Hello. Hello, everyone. Hello, Jisoo. So, hi, Sanghyun. Please turn on your camera. We're going to start soon. All right, it seems many of you are not turning on your camera now. So if you don't, I'm going to ask some questions. Okay. So in the last lecture, we started the video classification, and today we are going to go over the second part of that. So before we start, as usual, we are going to review the previous lecture. So let's start. Okay. Who didn't turn on the camera? Okay, let's see. 동건? 동건 Lee? I told you. Yeah, okay, cool. Yeah, in the last lecture, we learned about the video classification models. And we talked about score fusion and feature fusion. So can you explain what are they? Don't remember? Yeah,
Sorry.
it's okay. Okay, let's ask another student. Junsu? Im Junsu?
Yes,
Yes.
Professor.
Yeah, what is the score fusion and feature fusion? Well, it's not a difficult concept.
Score fusion.
Just as its name implies, what would be the score fusion?
Sorry, I was disconnected.
Okay. Okay, let me ask another student. 도균? Kim Do-gyun? Do-gyun, are you here? Yes. What is score fusion and feature fusion? Yeah, score fusion is score-wise aggregation, yes. For what? Of frames, yeah. For what? Okay, yeah, please study. Even though we are done with the midterm, we will have the final exam anyway. So, okay. So, what is the score fusion and feature fusion? What do we need? Why do we need that for what? We are dealing with the videos now, not a still image. And video, I told you, video is a sequence of images, right? And we would like to extract compact representation for each of the frames using some image models or 3D convolutions, not necessarily 3D, sorry, just convolutional neural networks. But because each frame is represented as a vector, now we have a sequence of vectors representing the entire video. And then we would like to map it to just a single set of labels. So how should we do that? We can extract the score for each of the classes for each of the frames, and then we can aggregate those scores, maybe taking average or max. Or we can fuse those feature levels. Maybe we can also take the max pooling or average pooling or some learnable method like the concatenation, and then taking the several fully connected more layers. There are a bunch of ways that we have discussed in the last lecture. So please review them if you're not familiar with what I'm talking now. Let's ask the next question. Let's see. Yurim? Che Yurim?
Yes, Professor.
Yeah. So for the feature fusion, we talked about late fusion and early fusion. So what's the difference? Just guess. Its name is really straightforward.
In late fusion is we aggregate the feature after taking component.
Yes.
And in early fusion, we aggregate the feature in low pixel.
Yeah. Not necessarily pixels, but we have multiple layers. Thanks, Yurim. We have multiple layers in the convnets. So if we take the fusion at the earlier layer, which means it's closer to the input side, that's called early fusion. And if we fuse at the very last or close to the last layer of the network, that is called late fusion. And we also discussed that it's also possible to fuse in the middle, right? Thanks, Yurim. And then we talked about two-stream approaches, and we have seen a few examples of that. So let me ask Uni.
Yes.
Yeah, what was the two-stream approach?
So there's two, like tower-wise network, which are spatial and temporal. And spatial tower is actually like just image classification, whereas temporal stream is like its input is several frames. And we compute like over optical flow from it.
Yeah, it's a perfect answer. Thanks, Uni. So two-stream approach, we build two separate streams. One is for learning the spatial patterns within the video, and the other is for learning the temporal stream, which means learning the temporal dynamics. So we train each of those separate networks independently, and in the end, we combine them as like average pooling or max pooling, and that's basically the idea of the two-stream approach. And using the optical flow is one example of learning the temporal stream. So which actually connects to my next question. So let me ask it to Ayong.
Oh, yes, Professor.
Yeah, what is optical flow?
Optical flow is the the motion, how the object is moving, or the
Yeah, I think you know the concept roughly. Yeah.
Yes, the direction that the objects move or the sometimes it show the brightness.
Right. Okay.
Yes.
So, so to be precise, it's a vector field that for each pixel where it's actually moving to the next frame. So we can compute the vector movement from the current pixel, and the location of that pixel, that part of the object where it appears in the next frame. Then we can actually point it out and then connect it as a vector, and that is defined as an optical flow. And we have seen some code that we can call some API functions from OpenCV, and we can compute the optical flow. So yeah, thanks, Ayong. And in the last question, Konstantin?
Yes.
Yeah, in the last lecture, we discussed about forced labor assignment problem. What is that?
We have, like, for example, when we have an action, there can be, we had this example of running and jumping.
Mm-hmm.
And we have an area in between those two actions. And there we somehow get a problem, but I don't remember exactly how.
Yeah. So yeah, thanks, Konstantin. So we, yeah, that was the example actually I used in the last lecture. So in the two-stream approaches, we in the initial models used only one frame of the entire clip or the video, and that particular scene may not contain the essence of that action labors, like jumping. So using that particular frame to represent the entire spatial signal may be misleading, because it doesn't basically contain the essential signal. So yeah, that was the forced labor assignment problem. Okay, thanks for everyone who answered. Yeah, if you are not able to answer some of my questions, even though I didn't call you, please study and review the materials, because it will be getting harder and harder, and it will be much harder to catch up near the when we get to the final exam. So you can always ask me to share the lecture recordings, and you can always review the materials. And if you have any questions, please feel free to drop by in the office hour to ask the questions, okay? Okay, so today, in the last lecture, we discussed about these four methods on the top, and we are going to study the rest of these in today's lecture. So let's start with 3D convolution. So before we start the specific method here, we need to learn about what is the 3D convolution. So in lecture 5, previously, we have learned what is convolution, right? And we talked about 2D convolution, which means the input is a two-dimensional matrix or image. And here, for example, it's an image of 32 by 32. And that means the width and height is 32 pixels. And because this is monotone image, we have just a single channel here. And we use 3 by 3 filter, and the meaning of the convolution is we convolve or slide over the image, spatially starting from the very first 1 to 3 and 1 to 3, and convolve over all possible spaces to the right and to the bottom, and computing dot products using all the matching numbers between this filter and this image. So that's what we are using as 2D convolution. 3D convolution is just simple extension of that. Now we have a video instead of a single image. So instead of a single image like this, we have 5 such images. So the input size is 32 times 32 times 5. Or actually, we use the time dimension first. So 5 times 32 times 32. We are going to use that. So here, instead of 3 by 3 filter, we also need the dimensionality or the coverage of the temporal axis as well. So suppose we have 3 here, then the filter will look like this. And each of these will correspond to 3 time index. So it will start from the first, second, and third frame, and then it moves to the second, third, and fourth, and then it will move to the third, fourth, and fifth. So just as what we did for the 2D, but it's just the idea is expanded to 3 dimensions. So instead of just spatially, we are going to spatio-temporally slide over the entire video. So here's an example. Suppose we have 5 times 32 times 32 video, and we are using the 3 times 3 times 3 filter. And then the very first one will be on the first 3 time indices, which is 1 to 3, and we are going to apply the 3D convolution like this. So these are all the 5 images we have in the input. And at the beginning, we start here. Time-wise, it's 1, 2, and 3. And spatially, 1, 2, 3, 1, 2, 3 for height-wise and width-wise. So we have total 9, 9, 9, so 27 values associated with this location, and multiplied by all of these values within this rectangle, this cube, and then sum all of them, and it will be just one value. So that will be written in the output. In the next, we move it to just spatially, so because we have to temporally and spatially slide over all the possible positions. So we are first doing the time 1 to 3 first, and this is same as before, as we did with the 2D convolutions. We move to the next position. So here, time-wise is 1 to 3, and in the height-wise is 1 to 3, but in the width-wise is 2, 3, 4. And then we move to the end, right? The same as just 2D. And then it moves to the second row and third row, and in the end, it will be located at the very end. Still, we are doing only with the first 3 frames, okay? And then we move to the next one. So now we do exactly the same thing, but not with the time index 1 to 3, but now we are doing it 2, 3, 4. We slide over in the temporal dimension as well. And in the same manner, we do this same thing for the 3, 4, 5. So starting from here, we are going to move until here. Okay, it looks complicated, but the idea is the same as 2D. Okay, everyone is following? Okay, it will be more complicated in the next slides. So yeah, before that, what is the final output size? I'll give you 10 seconds to think about, and I will ask. 지원? 강지원? Yeah, what is the output size here? No, with no padding. Think about this, everyone, and check if your answer is correct. What is the size if we just do this in 2D? If we slide over 32 by 32 image with 3 by 3, and then what is the output size in that case? 30 by 30, yes. And then how many output frames we are going to have in the temporal dimension? We are doing at the 1 to 3 first, 2, 3, 4 in the second, 3, 4, 5 and the last. So how many total? Yes. So the output looks like 3 times. This is the temporal dimension. and 30 by 30 is the spatial dimension, and 1 because we have just one channel. So now we have 4 numbers instead of 3 because we have the temporal domain here. And he asked with padding. So what if we have the padding size 1? The same question. Let me ask this to Kim Jin.
Yes, Professor.
Yeah, what is the output size if we use the padding size of 1 for all dimensions?
I think it's gonna be the same as input size. So
Yes.
5 times 32, 1.
Yeah, exactly. Why?
It's actually, I think it's just same calculation as to the convolution. So
Yeah, so padding size 1 is actually the same size padding when we use the 3 in the filter size. So actually, it's a very simple question. So you can preserve the input size by using the padding number 1 if you use the 3 by 3 by 3 filters. Okay, so let's move on to the next, a little bit more complicated version. So in the 2D convolutions, actually, we are using RGB images as input, not the monotone images, right? So that's how we're dealing with the color images. So we have 32 by 32 images, but we have 3 of them, 3 channels in the RGB inputs, right? So we were already actually using 3 by 3 by 3 filter instead of just 3 by 3 because we have the 3 channels in the input. So in videos, the input will look like this. So we have 5 images, and each of those images have 3 colors or 3 channels. So the input tensor actually looks like this: 5 times 32 times 32 times 3, because we have 3 channels. Okay? And now, suppose we are using the corner size 3 by 3 by 3 by 3, then here, the first one, the red one, means it's applied to the temporal domain. And in the middle 2, they are applied to the width and heights. Usually they are the same. And the last 3 is applied to the channel-wise. Okay? Looks complicated, but it's still just the same idea. So the question, we apply the 3D convolution on an RGB image like this, 5 times 32 by 32 by 3 video, and we use 4 3 by 3 by 3 by 3 filters. What would be the output size? 10 seconds. June, what is the output size?
It's 3 by 30 by 30 by 4.
Yes, correct. It's the same as before, but we have just 4 channels because we have 3 of these, right?
Yes.
Cool, thanks. And then what if we have padding size 1? Yeji? Yeah, what's the output size if you have a padding size 1?
It's 5 by 32 by 32 by 4 because it is the same padding and the output should be the same size.
Great. Yeah, I think you guys are understanding this. So yeah, it looks very complicated, and it was actually really complicated to actually create these images, but theoretically it's actually nothing. It's the same as the 2D, just a simple extension to the third additional dimension. Cool. So now we are going to use this as a building block to build our video classification models, which resembles the image classification models using the 2D convolutions. We're just extending it to the temporal dimensions. It will be very similar, but a little bit more complicated. So let's see. The first model is the C3D. It's actually 3D convolution networks. So it's C stands for the convolution. And we're going to see the R3D and R2 plus 1D. The R means ResNet. So they just apply the idea of the ResNet to this model. And T3D is a simple extension of these models. So we are going to actually look at these three models first. Before than that, in 2010, some guy proposed 3D convolution neural networks like this. So given some image of a video of 7 frames with 60 by 40, very small image size, and they applied 3D convolutions in a row like this, relatively deep neural networks to classify them. But unfortunately, this idea was too early. Like in 2010, we didn't have that much computation power. So this idea was not sensational because it wasn't possible to basically make this operational. So this idea was just first proposed like 11 years ago. But after that, the first successful model was proposed in 2014, end of 2014. So they applied 3D convolutions on video volume. And this paper is actually from Facebook. So they have a lot of data, video data, and computational power. So here's the method. It's just very simple. During the training, they use 5 random clips, 2-second long clips, which is very short, extracted from the video, and use the ground truth as the action reported at the video level. So ground truth is labeled only at the video level. For each frame, we don't know what it is, but because they just use very short clips, they just assume that the labeled action applies to all the frames within the video. So this is the model, looks like. So they stacked 5 layers of the convolutions, and each in the 3, 4, 5 layers, they actually stack 2 of them. So in total, they have 1, 2, 3, 4, 5, 6, 7, 8 convolutional networks, and then convolutional layers, and then 2 followed fully connected layers. So the entire network structure resembles that of AlexNet, right? They have conv1, conv2, and consecutive conv3s, 4s, and 5s, and then 2 fully connected layers. Just they extended the filter size from 2 dimensions to 3 dimensions here. 3D convolution corners 3 by 3 by 3, and stride size and the pooling layers use 2 by 2 by 2, and only the first one use 1 by 2 by 2. So what I actually would like to ask you is, just this figure contains all the details of this model. So we can actually reconstruct. You probably remember this kind of slides in the previous image classification lectures. So they stacked conv1, pool 1, conv2, pool 2, and blah, 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 until fully connected 7. And for each of these models, each of these layers, they specified all the number of filters, and the filter size is always 3 by 3 by 3. And stride size was 1 in both spatial and temporal dimensions. So they actually provided all the details in this figure. So can you try to fill out the entire table using the information? This, I'll give you like 1 minute. So be careful. In the pooling layer, first pooling layer, they applied different stride size, different pooling size for the temporal dimension and the spatial dimension. So it's 1 by 2 by 2. And after that, always is 2 by 2 by 2. Okay, let's do this together. Jayan? You, Jayan?
Yeah.
Yes. Yeah, what is the output size of the first conv layer?
It will be 64 by 112 by 112 by 3.
By 3?
Yeah.
Why?
The input dimension is 3 and stride 1 and padding 1 is applied to the input, so the output dimension is also be 3.
Okay, so what is the meaning of this 16?
The number of frames.
And here, and how many frames do we have?
Ah, I misunderstood.
Yeah, so
and
what, yeah, how many should we have here?
yeah, 16 by 112 by 112 by 64.
Yes, that's correct. Great job. Let's do one more. What about the pooling layer? So the input should be the same. And then what is the filter here?
The output shape should be same as the input
After the
shape.
pooling?
After pooling.
So yeah, the output size here is the same as input. That's except for the number of filters. So as you said, this should be 16 and 112, 112, and 64. And then we apply the pooling, which is this size, right? 1 by 2 by 2. So what would be the output size then?
It would be 64 and 56 by 56 by 64.
Yes, so 16, 56, 56, and 64, which means here the pooling layer 1 means we don't shrink the size. Stride is 1, so we apply the pooling, but steer is the same. But spatially, we are applying 2 by 2, so it reduces to half. So it would be 16, 56, 56 times 64. So great job. Thanks, Jayan.
Thank you.
So in the next slide, actually, I have all the answers. So you can check if your progress is correct. So until here, it's actually simpler. After that, they apply double number of filters of the same size, and nothing changes, but just the number of filters changes here to 128. And then apply 2 by 2 by 2, which means temporally and spatially everything is reduced to half. So it will be 8 times 28 times 28 times the number of filters, the channels. And in the convolution 3, it's the same, still the same size filters, and just number of filters got doubled, and only that part changes. And after that, they apply another 2 by 2 by 2 pooling. So the size is going to half again, and again at the end of the pooling 5. So the final output size is just one frame with 4 by 4 times 512 channels. And then it is fully connected to 4096, and again, another fully connected. And then it's mapped to the number of classes, which was about 400 for their data set. Okay? So, yeah, Young-Suk, do you have any question?
Yes, Professor, can you hear me?
Yeah.
Yeah. In this slide, I think the filter has 4 dimensions, isn't it?
Filter has 4 dimensions.
Yeah, because you consider multiple number of channel.
Yeah, that's automatically should be added.
Okay.
Yeah, we always should have the same number of channels for each filter, and that's not explicitly written here, but it should be reflected. just as for the 2D convolutions, we always said that like 5 by 5 conv. We just omit the number of channels because that's always the same.
Okay, thank you.
Okay, thanks. Okay, so to practice this, we are going to have this similar kind of questions in the final exam. So, okay, so this is another picture with, okay, a question from Dongwook.
Oh yeah, Professor.
Yeah.
I believe I missed a little, but can you explain about the padding of a final filling layer? Not a padding, maybe. How can it strike the final filling layer? Because we have 7 by 7 special dimension, but we have even number of stripes.
Oh yeah, that's a good question. There are multiple ways of dealing with them. So they might implicitly pad it to 8, which is equivalent to just taking, so for 7 by 7, we take the index 1 and 2, and it goes to the first one. 3, 4 goes to the second one. 5, 6 goes to the third one. And for the 7, we just pull only those 2 values, 7, 1 and 7, 2, something like that. So we can just use those partially available values to pull, or we can drop them. It's up to their implementation.
Thank you very much.
Yeah. So yeah, it's what is written in their paper. So it was like from 2 by 7 by 7, it goes to 1 by 4 by 4, and that's probably they have done like implicit padding. So this is the C3D network, very similar to AlexNet. So their limitations is, first of all, it's hard to model the long-range temporal relationships. They just did with 2 seconds long, very short videos only. So because the input was the 16 frames, they reduced to 1. But what if we give like 1,000 frames, more realistic videos? Then it will be just going to have 5 times. So it will be still a lot of frames in the end. So that means the temporal information is aggregated only nearby in the temporal dimension, not far away. So this model is not effective to learn long-range relationship, which will be essential if we deal with longer videos. And training such huge networks is computationally challenging. That's, you can easily imagine, because you already have done your homework, image classifier with 2D conv, and that took really long time, right? 3D conv, can you imagine how long it will take, especially using the computers in 2014? So it's really computationally challenging, and they needed some ideas to reduce the computational overhead. And I didn't talk about that, but at that time, they still used some handcrafted features, some pre-deep learning era features, and it was still stronger than just C3D models. So that was the limitations of this model. So they tried to reflect the ideas proposed in image classifiers, and they the next model from the Facebook was R3D. So that R stands for the resonets. So this is basically 3-dimensional resonets. So this is the 2-dimensional resonate we learned before in lecture 8. Here, they just expanded that idea to 3D conv. So here, I wrote in black color the original design in the 2D conv resonets, but I changed it to red color with the 3D convnets. So they stacked residual blocks up to 152 layers in the original resonets. But in this paper, they tried only 34, up to 34, because the 3D conv is expensive. So stacking like this high number of layers is not possible. And each residual blocks has 3 by 3. Instead of 3 by 3, they now have to have 3 by 3 by 3, 3-dimensional tensor as the residual blocks. And then they periodically, where the layer name changes, which when the color changes in this figure, like this, they marked like divided by 2, which means they use the stride size of 2 to reduce the size. So whenever the color changes, the number of filters got doubled from 64 to 128. and using this try size to reduce the size of the filter to half. And that's still the same. But in addition, they also reduced the temporal dimension as well, like using the 2x2x2. And at the very beginning, they used the stem conv layers, which using 7x7 convolutional layers. This is still the same. And this is just image models. So they call it conv1 here. And this is just an image model. And then they didn't use any fully connected layer in the end, and that's still the same. So basically, the architecture is same as the ResNet, but these minor straightforward changes, they apply the 3D convolution layers in the middle. So let's see their architecture. So this is the architecture table from the paper. So we usually specify the model architecture in this manner. So let's see. The input image size was number of frames times 112 by 112 by 3 RGB channels. And here L was, they used 8 or 16, just as the previous sys3D paper. Still very short video. And then conv1 is the stem layer. So they applied, actually, sorry, this is not just pure image model, but they actually used 3 frames at the same time. So this is actually 3D conv, sorry. So they applied 3 times 7 times 7 convolution layers to learn the basic features from this video. And they used the stride size of 1x2x2, which is the same as sys3D, which means temporal-wise, they don't reduce the length. So the output size is still the same in the spatial in the temporal domain, but they have reduced the sorry, this is from this L by this size, but now this output size output length is still L because they didn't reduce using stride or 1 for the temporal dimension. For spatial dimension, they apply 2x2, so the size reduced from 112 to 56 here. So that's the convolution 1. And after that, they applied like 3 in a row convolutional layers, the residual blocks. So here, the lighter version, they have 2 of them. In the bigger version, they have 3. So like this, they have 3 layers of this. And here, all the channel, all the filters were 3x3x3. And here, the output size is still the same because they applied let me think. I think the 1x2x2 is applied after this. Oh, yes. Oh, wait a minute. Sorry. So starting from this image, actually, this should be 3. Sorry about that. Yeah. So after the second conv, they didn't reduce the size by the pooling, according to this table. And only after conv 3, 4, and 5, they reduced the temporal number of frames and the spatial size to half by using 2x2x2 stride size here, like divide by 2, divide by 2, and divide by 2 here. So there, the size of the image, the features, and the length of the video got reduced to half. But at the beginning, I need to double check this. I'm a little bit confused here. But the basic idea is that once they change the color they reduced the spatial temporal size to half, everything together. And at the same time, they increased the number of filters from 64 to 128 and doubled here. And in the end, they take the average pooling. After all, they will have just 2 by 7 by 7 if they use 16 frames. And then they take the average to have just one number for each of them. And then they map it to fully connected layers with 1,000 class, 400 classes. So this is the ResNet 34 architecture extended to the 3D convolutions. And R2+1D is a simple extension of the R3D network. So it seems that their R3D paper was rejected from the conferences. And in the meanwhile, they also developed their next version, which was the R2+1. So the main idea is, instead of just convolving with the 3D convs at once, they conducted 2D conv first on the spatial domain, and then followed by 1x1 conv to reduce the dimensionality on the temporal axis. So you may be familiar with this idea. It was first introduced in Inception V3. This is the Inception V3 we talked about in lecture 8, at the end of lecture 8. So 3x3 conv can be reduced, actually split into 1x3 or 3x1. It's the two dimensions in the spatial domain. They horizontal and the vertical, they split like that. And they still have the same receptive field size. That's what we discussed before. But this one has less number of parameters and more number of nonlinear activations. So it was more efficient. That's what we discussed before. So they apply the same, exactly the same idea here to reduce the T by T by D, the temporal times spatial to axis. They reduce it to spatial first, and then temporal only. So that's why it is called 2+1D. But basically, they have the same representational power, but it's much more efficient. So here's their experimental results. So when they trained R3D, which is the blue color, and R2+1D, the red color, both the training and validation errors actually get lower at the same number of epochs. So why is this good? So the model is forced to explicitly learn temporal dynamics and spatial appearance separately, which is actually makes sense, because suppose that this three-dimensional tensor, 2 dimensions of them represent a spatial information. So 1 pixel difference means some physical distance in the real world. But in the other dimension is temporal dimension. So 1 pixel difference there means some time difference. So physical meaning is different. In 1 dimension is time, and the other 2 is the space, which is not natural. But in this way, it's separated. So some part of the network is forced to learn only the spatial dynamics, and some other parts only learn this temporal dynamics, which does not mix to each other. So that's more natural, and this is basically the similar philosophy to the two-stream approaches. So that's one guess by these authors, by the way. And double nonlinearity. So we also talked about this before. So because they have 2 separate layers instead of just a single 3D conv, they have more nonlinear activation functions, but still have the same representational power. So that was their main motivation. And actually, I recommend you to read both of these versions of this paper. So their first draft is only available on arXiv. I guess they were rejected from any conference. And then they got accepted as CVPR with including this R2+1D. And T3D is another 3D convolution networks based on DenseNet. We didn't explicitly talk about this DenseNet, but that's actually a simple extension of ResNet. In ResNet, we have the skip connections, you may remember, to force the network to use the capacity of the layer only if that's really necessary, right? But in ResNet, they have the skip connections only to the next, right next layers like this. The skip connections is connected to just skip 1 or 2 layers here. However, actually just skip only 1 layers here. But in DenseNet, within the DenseNet box, we have multiple layers, and we have the skip connections for all possible pairs within that box. And then those kind of boxes are stacked multiple times. So you can think of it as just a simple extension of the ResNet, but it's much more powerful. So this is based on this kind of DenseNet. So it looks like this. So they stack these dense blocks. Within these, all the layers have the skip connections for all possible pairs of the layers. And their main idea was having temporal transition between these dense blocks like this. Looks familiar, right? We have seen something like this before. 1 by 1 conv, 3 by 3 conv, and it's 3 by 3 by T3. It's not 5 by 5, but T temporally is different. So, and then they concat the results. What was this? It was called Inception, right? The GoogleNet. So they had 1 by 1, 3 by 3, and 5 by 5, and the pooling, and then they concatenate them, right? So they just apply this Inception modules idea here. And in that way, they were able to actually learn different spatial and temporal range of the objects or actions. And they just combine them to detect the actions spanning longer time frames or its shorter time frames. And for the objects as well, the small objects and the bigger objects at the same time. And this is more about the details of how they train the model. So they use the pre-trained 2D models as kind of teacher to force the middle-level features to be similar to what they have learned using 2D image data. So for the details, I would like to ask you to read the papers. They actually have a very interesting idea to teach, they train these 3D conv models because they didn't have enough data. So if we have infinite amount of data, video data, and we have infinite amount of computing powers, it's always good to just let the model knows everything by themselves. But with limited data and limited resource, it's not possible. So they use some trick to force the embeddings to be similar to what they have learned with image models. So that's the T3D models. And now we have the 2-stream models and the 3D conv-based models. And then people try to combine the ideas which were kind of independently developed in 2 different communities. So I3D is one of the widely used video features still. And some simple extension of that is S3D. So let's talk about that. So by the way, the author of this I3D is the same guy with these 2-stream models, Alex Seiserman from Oxford and DeepMind. So they took basically the idea from the C3D to combine with their original idea in the 2-stream methods. So let's see. So what was the 2-stream method? We talked about this in the last lecture. So from the video, we take just one image to learn the spatial patterns using some image models. And we compute the optical flow for all the frames in the video and use only 2D convnet, applying that each of these frames as just as the channels. So they only use the 2D convnets, and the 2-stream was the image model based spatial stream and optical flow based temporal stream. So that was the 2-stream model. And they extended this idea to multiple ensemble of them, basically. They used different imagery and optical flows from different parts of the video and then they combine those to have the final scores. So that was the extension of their two-stream fusion. But still, it was based on, each of these models were still based on the 2D convnets. And C3D is what we just discussed. So from the image, we just applied some 3D convolution operations to run the features directly. So here's their idea of combining these two. So from the for the spatial side, they use the 3D convnets instead of using just a 2D convnet with a single image. Now they use all the frames and apply the 3D convnets. And for the optical flow, they still use the optical flow, by the way. From the optical flow, they also apply 3D convnet instead of treating all of these images as different channels. So yeah, here's the more details about the idea. So from the first two-stream method, the spatial stream was just a 2D convnet image model, but they extended it to 3D conv, so they directly digesting the sequence of RGB images. And this part, with only this part, that's same as C3D. And for this part, they still use the optical flow, but instead of taking each of these as different channels, they actually apply the 3D convnets to take advantage of the actual sequence or actual order of those frames. So that's their I3D model. And for their backbone, they use the Inception module. So this is the Inception module we learned before. Remember? The left is the 2D Inception module we have learned. And to recall, they have 4 paths. One is the 1x1, 3x3, 5x5, and 3x3 max pooling. And they applied 1x1 conv to reduce the dimensionality and the computational overhead. Remember? They applied the same idea using the 3-dimensional conv, 1x1x1, 3x3x3, and it should be 5x5x5, but I don't know why, but it's 3x3x3. It's the same. So I thought that this is a mistake in the paper. So I actually searched the actual code from the DeepMind, because I'm working for Google. I can do that. And it was actually 3x3x3. I don't know really why, but they actually did that. So it's not a mistake. It's probably, I don't know. I don't really know what happened here. But they actually did this. And the max pooling is also 3x3x3. So this is the 3D Inception module for I3D. So you may remember that this is the two-dimensional original GoogleNet using the Inception modules. So we have learned that we have the STEM network at the beginning, and then we have stacked Inception modules 9 times. And in the end, they have the classifier. You may remember this from the previous lecture. So this is another way of drawing the model. It's still the 2D original GoogleNet. So this part is the STEM network, same as the previous figure. And then all of these are the 9 stacked Inception modules, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And then this part is the classifier. So this is a more simpler way of presentation of this network. And I3D just extended this model to 3-dimensional. So just compare this. 7x7 conv. They have now 7x7x7. And the max pooling is 3x3. Here is 1x3x3. So it's basically just the image model. And then 1x1 conv becomes 1x1x1 conv, and so on. So they just extended this model to 3-dimensional. For the details, please check. So it's the same. So STEM network, and then stacked 3D Inception models, and then classifier. And the number of layers even is the same. So I3D is basically just the Inception network or GoogleNet, same as before, but only some of these are extended to 3-dimensional conv layers. So someone may ask that, do we still need optical flow? Because we talked about the downside of using optical flow. We have to pre-compute that using some deterministic algorithm, and we have to store them in the disk. And because we have the same number of frames as the input video, that we require the same amount of disk storage to store them. We have to pre-compute them. So it's really inefficient. We really don't want to explicitly compute the optical flow and store them. We just want to the model to actually learn it. But even until 2016 or 17, it was not possible. So the authors guessed that with 3D conv, RGB may be sufficient, but until that time, it was not possible to surpass the performance. Then they used the optical flow. So it's what they guessed. So the 3D convnet still performs pure feed-forward computation. So we just feed some input, then it computes the operations, conv operations in one way, and that's it. It just outputs something. But optical flow is basically estimating the difference between two images. So the algorithm actually has some recurrent aspects of that, some iterative updates. I don't go over the details of this, but if you are interested in, you can refer to the section 2.4 for more details about this discussion. After this, nobody uses optical flow in regular video classification models, because now we can surpass using the C3D or R3D using much of the data and computing resources. Okay, and let's move on to S3D. This is still really similar to I3D, but just a slight change. So for the R3D, we have changed it to R2 plus 1D by just splitting this 3D conv part to spatial first and then temporal, right? It's just that idea. So convolution is 3 by 3 by 3 in this Inception module. They just split into 1 by 3 by 3 and 3 by 1 by 1 in a row. That's the only difference. Done, okay? But they argue that this is much more efficient. And here it's still the same number of layers and same styled, exactly the same model. But only difference is that this Inception module is changed to this one. And here, this SEP conv 3 by 3 by 3 is also split like this. So that's the only difference. S3D is lighter model, lighter version of I3D. And I personally know the author of this paper. He was a really productive engineer and researcher at Google. He recently got a position in Brown University and became a faculty member there. So yeah, he's a very smart guy. And this very simple idea, he achieved much more efficient model and the better performance. And he was able to publish this paper, so which is a great thing. Okay, we have 12 more minutes, and let's finish the remaining models quickly. So I'm going to talk about the slow fast model and X3D models to finish these slides. Slow fast networks is actually really innovative and interesting two-stream models, but it's just based on the 3D conv. So let's see. They don't use even the optical flow. So given a video, you prepare two streams by sampling with different sampling rates. So in the slow pathway, we sparsely sample the input frames. For example, they use 16, they sample one frame for every 16. So every 16 frames, they just take one regularly. For the higher frame rate part, or the fast pathway, we take the frames more frequently for every 2 frames. So for every 2 frames, we sample one. So it's 8 times more frequent sampling. It's the higher frame rates. And then they train the model separately using different architectures, very similar but different architectures. And then the prediction of each pathway is combined using some pooling. So let's see their architecture in more details. Looks very complex, but it's not actually. Let's see. In the slow pathway, the given video is sampled at every 16 frames. We sample one frame. So this is the one. So in their input, actually the stride size is 16, and the for the pixel-wise, they don't sample, so it's just 1. And for the fast pathway, they have 8 times more density sampling rates. That's what I already talked. And then in the next convolution layers, they apply convolutions. But here you see that it's 3D conv, but the first dimension means it's the temporal dimension, right? It's 1 for most of these layers, which means they are basically doing the image-wise, just frame-wise convolutions, except for these 2. So in this slow pathway, the temporal mix is happening only in these 2 layers. Actually, it's multiplied by 6 on 3, so it's more than 1. But all other layers are just image-wise applied. So in this slow pathway, you see that the 3D filters across the temporal dimension are limited used, and it's just purely, not almost purely based on the images or just nearby frames. Instead, in the fast pathway, you see that this temporal domain, more larger than 1 filter size is used at all conv layers. So here is starting with the 5 consecutive frames are convolved at conv 1. And then in the conv 2, conv 3, 4, 5, they always mix information from adjacent frames. So because these are nested, actually the receptive field is larger than 3 consecutive frames. So here, because we have more frequent number of frames sampled, they are mixing those informations with more layers. And the last number means the number of filters or number of channels. So here they use the user number like 64, 128, and these numbers. So in the end, they have just 2048 channels. But in the faster pathway, they have 8 times smaller number of channels because they have 8 times larger number of input frames. So they reduce these weights, the number of channels, to have this maintain this network is more lightweight. So in this sense, actually, the computational overhead in slow pathway and the fast pathway is similar. And this is more about the details of the training. So you may be interested in what are these, the red arrows here. So without this, these 2 pathways are completely independent. But what they tried is actually crossing. So after some blocks, here the blocks means res 3, 4, between these 2, the architecture changes. So this is repeated 4 times, for example. This is repeated 6 times. But between these 2, that's between these 2 different blocks. The faster pathway uses the slower pathways feature and vice versa. They tried to mix them to the other stream, but they realized by experiments that using this one in the fast pathway is not that helpful. So they only applied this lateral connection from the fast pathway to slow pathway. So that's just the main idea of this, and I wrote some details about that. To implement this, the feature size should be the same as last time. Otherwise, it's not possible to combine. So except for the number of channels, everything else should be the same to concatenate them. So it's talking about the details of that. So if you're interested in, please read the paper, section 3.3. It talks about how they apply these lateral connections in more details. And the last model we talked today is X3D, or Expand 3D CNN. So it's still by the same company, Facebook. So inspired by feature selection methods in machine learning, they apply some stepwise or greedy network expansion from very simple models. So here's their architecture. So here, instead of having some fixed number, they actually have many different variables included in this table. It looks very similar to what we've seen in the previous slides, but it's much simpler structure. Many of them are just ones or very basic numbers. and multiplied with some other 6 variables here. So these variables are controlling which part we have to increase. So for example, starting from very small number, they try to increase, for example, the number of channels or the number of strides or output size, everything described here. So in the next slides, actually, they have the results. So they start with 2-dimensional basic model. So everything here is the default value. Probably most of them are just 1. And then they try to increase all of these 6 slightly and see which one is actually contributing improving the performance as mostly. And then they choose one of them. At the first, for example, this gamma D, which is expanding the depth of the network, was the most useful. So they just take that step, and then applying all of these 6 again, and to see which one is most improve the performance, and so on. So they computed that many times with all of these variables, and followed by taking the best one every time to improve the model until this point. So in the meantime, they chose some representative model as their most efficient one, like the X3D is X small, medium, large, and X large. So in this way, they improve the performance of the network by greedy incremental improvement of the model. So this one is their state-of-the-art model. And video models are, a lot of video models are proposed these days. So in this slide, I actually took some picture from this survey, so that was actually published at the end of last year. So this is kind of brand new survey paper. And these boxed models are what we already covered in this lecture, in the last time and today. So if you are interested in, you can also refer to other papers, especially the recent ones. Like there may be more interesting ideas there. But we have already covered most of these important models. And yeah, that's the current status of the video models. So you may see that compared to the image models, this is more like primitive. And actually, a lot of simple ideas are not being tested in video domains because of the lack of the resources, basically, and the lack of the data, as I told in the last lecture. So that's it. So yeah, this is the last slide. And in the next lecture, in the next 2 lectures, we are going to talk about the RNN and RNN-based video models. So RNN is recursive neural networks. Probably many of you already are familiar with that. That is RNN or RSTM is the most widely used model to deal with sequences of something, like the sentences, which is a sequence of words. So video can be seen as a sequence of images or sequence of vectors, and we can use RNN-based models to model the videos. So in the next 2 lectures, we are going to learn about RNN-based models. Okay, so this is it. And if you have any questions, please feel free to ask now.
Professor, can you hear me?